Shekhar. So do we have time to talk to him or?
No, I was actually going on to the last talk
Okay, okay.
because Mamta Sahu had to leave because of technical difficulties. So maybe, if Mamta's talk
Hi,
doesn't
yeah.
work, we'll come back to you. Okay.
Hi, yeah,
Yeah.
thanks. Actually, yeah, I'm sorry for the inconvenience, but there
No
was
problem.
heavy rain, so that's why it was not audible.
I
But we can try
understand
it
that.
again now.
Yeah, I
Okay.
think you'll be audible now because I think Unna will share your slides, right?
Okay. Yeah,
Yeah.
I think that's
Okay.
what she told
Then I
me.
think we can start again.
Mm-hmm.
So can you see my screen now?
Yes. Yes.
Yes. Can you see
Okay.
the talk?
Yes.
Yeah.
Is it fine? Okay.
Okay. Okay. So let me first thank the organizers for making me part of this conference and giving me the opportunity to speak about my recent work. So I'll be talking about inertial active constant envelope particle under the action of magnetic field. So already we have heard a couple of talks based on the active matter. So Una, can you just go to the next slide? Yeah. So these active matters are a class of system which are inherently driven far away from equilibrium, and the constituents of the active matter they are capable of self-propelling by their one, and they consume energy from the environment and they generate a spontaneous flow in the system. So basically, there are some examples of the active matter systems, which are plucking of birds, school of fishes, and also these the tissues inside living cells, and so on. So there are some standard models already exist, which are used to treat the dynamical behavior of such systems. They are ABP model as well as the EUP model. So this, but actually, this in ABP model, both the translational as well as the rotational diffusion of the particles are taken into account. Whereas the in AOUP model, the translational velocity this follows the AOUP process. But whatever is the discussion is exists in the literature so far. Most of the systems, active matter systems, they are based on the overdamped systems. For the particles who are macroscopic in size, if they are self-propelling in a lower viscous medium, then the inertia becomes prominent. And the inertial influence, they poses some challenge in the dynamical behavior. So this inertia can be included in the standard models. And in recently, the inclusion of inertia in ABP, they resulted some new phenomena, which are this inertial delay, as well as the some motility induced. Please go to the next slide. Motility induced phase separation and so on. So motivated by these recent findings, we are mainly interested. Please go to the next slide. Motivated by this recent findings, so we are mainly interested how the inertial influences the modulate the dynamical behavior of such systems. So next, actually, but at present we are mainly interested at the single particle level. So next slide. So actually, although the charged Brownian particle, the dynamics of charged Brownian particle in a magnetic field, although it is an old problem, but we are mainly interested in the dynamics of an AOUP particle when it is confined in a two-dimensional harmonic well and subjected to the presence of a magnetic field. Magnetic field is applied in the Z direction. So the dynamics can be described by the Langevin equation of motion. So this is the inertial force, and this is the viscous, the second term in the right hand side of this is the viscous force, which is due to the interaction of the particle with the environment. And this is the Lorentz force, which is due to the presence of magnetic field. And this is the force existed by the harmonic confinement, where K is the harmonic constant. And this is the basically the noise force, and D is the strength of the noise. And this noise follows the AOUP process. This noise is basically follows the Ornstein-Wolbach process or AOP process, and the noise correlation it decays exponentially with the noise correlation time Tc. So this is the time up to which the correlation persists or activity persists in the system. So with this model, so first we simulated. Please go to the next slide. Yeah, first we simulated the dynamics as the trajectories, especially for the case when the particle is set as free as well as when the particle is confined in a harmonic well. So we are mainly interested the transport properties and looking at the transport properties as well as the dynamical behavior with the magnetic field. So what we observe here for the case when the particle is free, then with the magnetic field, the particle is actually it's confined to a very small region. So under the action of strong magnetic field, the directional movement of the particle it gets suppressed, and the particle as if it gets trapped within small region. But for the case when the particle is confined in a harmonic well, so when the strength of the magnetic field is low, so particle precesses as usual across the magnetic field before coming back to the position where it was initiated. But when the strength of the magnetic field is very large, then the particle precesses across the magnetic field over a long interval of time, and also on average covers a large distance before coming back to the position from where it was initiated. So in order to understand this proper transport behavior, so we just simulated and also exactly calculated the mean displacement. And here I have shown the parametric plot for the case when the particle is set as free as well as for the particle when the confined in harmonic well. For the case of a free particle, and this color map, this shows with the time evolution, and we observe that particle evolves with time, and in the long time limit, it saturates a finite distance. So the mean displacement evolves in the long time limit. It just becomes a finite value, and it depends on the magnetic field as well as the inertia of the medium. Inertia of the particle. So next, when this mean displacement, when it evolves with the magnetic field, we observe that it evolves. It approaches zero value. Similarly, when the mean displacement with the viscosity of the medium, it approaches zero. But for the case when the particle is confined in a harmonic well, then the particle on average, it comes back to the position where it was, it has initiated the motion. So that means the mean displacement in the steady state limit and the long time limit is approaching zero value. So next slide, please. Yeah. So next we are interested in the steady state correlation. So what we observe here, the steady state correlation, this just for the case when the particle is confined in a harmonic well, the steady state correlation for the position, it persists for longer interval of time with the magnetic field, whereas the velocity correlation, it decays faster with the magnetic field. That is what I expected. But when the viscosity of the medium is very large for a highly viscous medium where the inertial influence are ignored, then in that case, the magnetic field has no influence on the correlated behavior of the position as well as the velocity. Whereas the position correlation and velocity correlation, they get suppressed with the harmonic confinement of the particle, whereas it persists for longer interval of time with the persistent time scale or with the noise correlation time. Next, we are interested, next slide please. Next, we are interested in the mean square displacement for the case when the particle is set as free as well as when the particle is confined in the harmonic well. So for both the cases, the initial time regime of the mean square displacement, they are ballistic in nature, whereas the steady states are not similar. For the case of a free particle, the steady state is diffusive in nature, and for the case of confined harmonic particle, this is non-diffusive. What we observe here that the steady state mean square displacement, it gets suppressed with the magnetic field, and for very strong magnetic field, the mean square displacement approaches to zero value. Whereas for the particle, when it is confined in a harmonic well, the magnetic field, the mean square displacement gets enhanced with the magnetic field. And for a very strong magnetic field, it saturates to a finite value. And this value becomes independent of the magnetic field as well as it becomes independent of the persistent times or noise correlation time. So this at this and the same value we obtain in the white noise limit, or when the TC tends to zero limit. So this is basically the particle behaves like a passive particle. So that is in the steady state of the confined harmonic particle. It is just makes a transition with the magnetic field. A strong magnetic field allow the particle to behave like a passive particle. So this is one of the interesting things which you see here. So next, actually, this the mean square displacement, when it evolves with the viscosity of the medium, then both the cases it gets suppressed. Whereas for the free particle case, even if the activity persists for a longer interval of time, the long time limit, the mean square displacement becomes independent of this correlation time. But for the case of confined harmonic well, it gets suppressed with the persistent time scale. So let me summarize what I spoke so far for the model. So one of the important thing that the inertia plays an important role for the magnetic field to influence the dynamical behavior of the system. And for the case of the free particle, in the steady state basically is diffusive as usual, and but with the magnetic field, the mean square displacement gets suppressed and approaches zero value. But for the case of confined harmonic particle, the mean square displacement get enhanced with the magnetic field, and for a strong magnetic field, it gets saturated to a finite value, and that value becomes independent of the magnetic field, and that is the same as what we get in the white noise limit. And the particle behaves as if like a passive particle. So the steady state basically it just is different from the free particle. So it's just like there is a transition with the magnetic field from passive to active behavior. So next, finally, I would like to acknowledge my PhD student, Mohammed Musin A, which is involved in this work. And this work, manuscript, we are yet to publish it. So thank you all for your kind attention.
Thanks, Mamta. Are there any questions? So Mamta, your steady state velocity autocorrelation functions, I think if I saw it right, I mean it went to lower than zero in in the presence of the magnetic field. So why this? Why do you see this?
You mean that this is due to maybe that you mean that the fluctuation in the
at long times it seems to be anti-correlated.
Yes, so that approach is zero because all the time scales means it's a system relax in the longer time.
No, but why is it negative?
Why is it negative is the question.
That is because this fluctuation, because I mean, yeah, this is an anti-correlated actually. So this.
So what does that mean?
Yeah, maybe that is the one time there is complex interplay between these time scales. So maybe that is due to the because there so we are not we cannot understand this. There are many scales involved here. So due to the harmonic confinement of one dominates with other, or because of that it may be and when the long time limit, when it dominates all other time scales, so system relax and then becomes it approaches zero.
Thanks. Abhishek has a question.
So this plots that you show, these are all analytic, right? Is that right?
Yes, these are both analytical as well as simulation.
Okay, the solid lines are analytical. Okay, and so the steady state. I mean, also I guess you have probably a closed analytic form, right? It's just Gaussian.
Steady state, yeah, I think it is a whole Gaussian, yeah.
Okay, but it's not. You can't write it as the thermal state, I guess, right?
No, it's not thermal
With
state.
some effective temperature, that's not possible.
Yeah, but here, yeah, I think this is, but there are in different limits, maybe that, for example, like in a strong magnetic field, in the magnetic field is very large. In that case, the harmonic confinement is ignored. So in that case, maybe it will be Gaussian, the distribution. So.
Okay. Yeah,
Are
thanks.
there any other questions? If there are no more questions, so there is a request from an organizer to ask if Shubhranshu will still ask his question to Manas.
Yes.
Okay, thank you.
Thanks, Mamta. Thanks a lot. Shubhranshu, are you there?
Yeah. Is Manos
This
there?
is from the
Yeah,
last
yeah.
talk. Yeah.
Okay. Manos, can you hear me?
Yeah, please.
Okay. So my question was that throughout your talk, I understood that you had the snapshots you talked about 15 frames per second or so, something like that. So
Yeah.
they are experimental results and
Yes.
pictures are experimental. But
Yes.
once you said that you did simulations as well.
The simulation was done only to figure out the maximum possible area fraction for a given range of orientational diffusion, because we need to compare the. Yeah, please go on.
I was inquisitive that in the simulation, two-dimensional simulations,
Yeah.
how do you actually incorporate this? The corners, you said these squares are without sharp things, sharp corners.
Yes.
So in
As I
simulation,
said,
that
that
should
this
be
is
very
this is very
difficult.
important. So in the simulation, Debojit has fitted the photo or the micrograph of each particle to get the corner rounding. So he uses an equation. There is some parameter called m, which defines the corner rounding. So he gets this from the actual particle and then uses the same value for the simulation. So if we change that value, then the plot will change.
So you have both translational diffusion as well as rotational diffusions for the particles, for the square particles.
In the simulation or
in the simulations, of course, yes.
in the simulation, we first impose the orientational diffusion, which is theta r that we measure, and then we see that how close the particle can get with that with that much orientational diffusion. From that, we calculate the maximum allowed area fraction.
And last question is, everything, your results will change. Do you expect to change if you take, instead of squares, if you take any other shaped object like pentagon or hexagon, say, or
So
some other thing?
phase behaviors are different as people have studied those systems, but this interdigitation and their orientational diffusion will always be important in those systems, and the equilibrium phase behavior will change. But I think the process that the orientational dynamics plays an important role, that part remains the same.
Thank you very much. It was an interesting talk. Yes.
Okay. So let us end this session by thanking all the speakers. And let me also, this is the last academic session, so let me also thank the organizers. And now I'll hand it back to the organizers for the closing session.
Yeah, okay. Before we go to the closing session, I request all of you to just switch on your video so that we can take a group picture. That's the best way we can do. Like, please do that. And then we'll go to, please switch on your videos. We'll just take a screenshot. Yeah, please, Avik, Edwin, Anulava, Rasmi, please switch on your video. Rita, Urna, please. Sita, Abhishek, please switch on your video.
They're all on, PK.
Oh, they're all.
Yeah, we're on.
Okay. So I'll take
Ranjini has switched on.
I was always switched on.
Okay. Okay.
Session
Some pictures
privilege.
and yeah. Okay. So so now I have this pleasant job of closing the conference on behalf of the conveners. So this conference series started in 1991. Professor Bikas Chakravarti and Professor Manna, SS Manna, who was here just talking now, has been an integral part of the conference from that time, and we thank both of them for their active support for this online meeting. And we also thank Professor Tanushree Sahadasgupta, Director of SN Bose National Center for Basic Sciences, and Professor Saurabh Pal, the Director of Indian Institute of Science Education Research, Kolkata, this place, for encouraging us and providing funds and support. We also thank all the speakers of the conference who took painful effort to speak in this meeting, because it's sometimes an odd time. So this brings us a huge number of registered participants because of the speakers. And special thank goes to the special sessions, which are by Professor Giorgio Parisi and Professor Deepak Dhar. And for their contribution, we certainly thank them. And a very special thanks goes to speakers who had to speak at odd hours, that is beyond their normal office hours. So thanks to all of them. And in a conference, particularly when it is online, maintaining time is very crucial. And we thank all the session chairs for a fantastic management of all the sessions. So the most important part is the technical support on an online meeting. The technical support is very important. And just because we hosted it and we live stream also to YouTube, so we thank the student volunteers and office staffs of ISAR Kolkata who worked very hard to just observe this. We thank others for managing Gather Town remotely from Bangalore, because he has some personal issues, he has to go to Bangalore, but he supported us very well. Thanks to Abhishek and Adway, who relentlessly monitored Google Meet and live streaming the YouTube. They have been here in the next room and the control room, and really big thanks to them. We also thank Indranil, who actively overlooked all these processes. A big thank to the technical support staff of ISAR Kolkata, Mr. Faruqi, who is our main technical staff, and Mr. Rajat. Without their help, the hosting would not have been possible. And also I thank Tanvi, Sangeeta and Munnada at ISAR Kolkata, and Sarath at SN Bose Center for arranging and maintaining the offline display locally. So we have a display board and with a big screen for local participants. So finally, a very big thanks to the organizers of this conference, Professors Krishnendu Sengupta, Arnav Sen, Avik Basu, Shashi Srivastav, and Ananda Mohan Ghosh, who helped us making several important decisions during the meeting. At last, and not the least, I thank Dr. Urna Basu, who has been acting as a backbone of this meeting. Single-handedly, she made the web page, posters, banners, and managed a huge number of emails by herself. Thanks, Urna. Finally, I would like to thank the participants of this conference for their active participation in oral and poster sessions. And I hope that all of you enjoyed the meeting, even in absence of Kolkata sweets. Okay, thank you all. And before I make my last remark, I should. It's a great pleasure for me to announce this. I would like to take this opportunity to announce the next StatPhys Kolkata meeting as well. So we plan to organize StatPhys Kolkata 12 at the end of 2023. And we hope to see you all there again. Okay, so we will also send you a form for your comments. So I'll stop here. Thank you all.
Thanks, PK. Yeah, it was
okay.
great.
So